Welcome to Night Cosmos Sleep. At this very moment, engineers in a control room on Earth may be sending a command to Voyager 1. The signal travels at the speed of light, yet it still takes more than 23 hours to reach the spacecraft, now more than 25 billion kilometers away. If Voyager responds immediately, its reply needs another 23 hours or more to return. A simple exchange can stretch across nearly 2 full days. What makes this even more remarkable is that Voyager can still understand those commands, even though it was built in the 1970s with far less computing power than many electronic devices we use today. After almost half a century, both Voyager spacecraft are still moving onward, even though their cameras were shut down long ago and their power supply grows weaker with each passing year. What they send home now is no longer imagery of distant planets, but small streams of data about magnetic fields, plasma, and high-energy particles in interstellar space. Before becoming faint whispers in the darkness, Voyager carried humanity closer to Jupiter, Saturn, Uranus, and Neptune. The spacecraft witnessed enormous storms, volcanoes erupting on a distant moon, and worlds unlike anything people had ever imagined. What did Voyager truly discover? How did a mission designed to last only a few years survive for nearly half a century? And what will happen when the final signals from these two spacecraft no longer return to Earth? Before their voices faded to what they are today, Voyager began its journey because of a rare opportunity in the sky, an alignment of the planets that humanity must wait nearly 2 centuries to see again. Imagine a radio operating from so far away that even its light takes nearly a full day to reach Earth. Out there, Voyager 1 is still moving onward, while Voyager 2 follows a different path, though it too has traveled far beyond the planets that were once its original destinations. Nearly half a century after leaving Earth, the two spacecraft remain the most distant messengers humanity can still communicate with. The average distance from Earth to the Sun is known as 1 astronomical unit, equal to nearly 150 million kilometers. Light takes just over 8 minutes to cross that distance, but Voyager 1 is now more than 170 astronomical units from the Sun, while Voyager 2 has traveled beyond 140 astronomical units. These distances continue to change as Earth moves and the Voyagers keep receding. But for Voyager 1, the one-way signal travel time has now grown to almost an entire day. Radio signals move at the speed of light, the fastest speed at which information can travel according to our current understanding. Yet, no amount of speed can erase distance. When an engineer sends a command from Earth, it does not instantly appear inside Voyager's computer. It must race across the vast region of space where the giant planets have long since been left behind. Nearly a day later, the signal finally reaches Voyager 1's antenna. If the spacecraft responds immediately, its reply requires a similar amount of time to return. A simple operation can therefore become a wait of nearly 2 days. This makes controlling Voyager entirely different from the image of someone holding a steering wheel. Engineers cannot see the spacecraft in front of them, nor do they receive live images showing its condition. Before sending a command, they must simulate how computers nearly half a century old will interpret each sequence of code, calculate which systems will activate, how power levels may change, and whether the spacecraft will remain properly oriented. When the response finally returns, all that appears on their screens are temperatures, voltages, equipment status, and scientific measurements. In a conversation this slow, patience becomes part of the engineering itself. At the other end of the link is a dish-shaped antenna 3.7 meters across, mounted on Voyager. It receives commands and sends data back home. The spacecraft continually adjusts its orientation to keep the face of the antenna pointed toward Earth. In the near vacuum of space, Voyager does not need to keep firing its engines in order to continue moving. But to remain in contact, that dish must stay aimed at an increasingly tiny target far behind it. A large enough error could prevent the signal from reaching the receiving stations. Voyager would still exist and continue traveling, but Earth would no longer be able to hear it. Earth receives that distant voice through NASA's Deep Space Network. Its 3 antenna complexes are located near Goldstone, California, Madrid, Spain, and Canberra, Australia. They are positioned far apart so that as Earth rotates and one station begins to lose Voyager below the horizon, another can prepare to receive it. When Voyager's time arrives, the enormous dishes turn toward the correct region of the sky, and computers begin searching for a signal so faint that, without knowing exactly where to listen, it could easily be mistaken for background noise. Voyager's signal is weak not because the spacecraft has stopped trying. The energy in its radio waves spreads outward as it travels through space, much like ripples on a pond expanding as they move farther from their source. The portion of that energy that reaches Earth therefore grows smaller with distance. By the time Voyager's signal arrives at the Deep Space Network, it may be tens of billions of times weaker than the power required to operate a digital watch. Extremely sensitive amplifiers, encoding techniques, and noise reduction systems allow the stations to recognize that whisper. It is like someone speaking very softly from the far side of an ocean with no shore, while the antennas piece together each tiny fragment to understand that the speaker is still there. Voyager's data rate is far lower than anything we are accustomed to on Earth. A video here may contain millions of bits of data every second. With Voyager, the goal is not to transmit as much as possible, but to make sure that the few available bits arrive accurately. Some channels send engineering data at only a few dozen bits per second. That is nowhere near enough to carry a video, but it can still reveal how the magnetic field around the spacecraft is changing, how plasma is fluctuating, or whether high-energy particles are passing through an instrument. A small stream of data can still hold enormous value when it comes from a place no other machine has ever measured directly. By the middle of 2026, Voyager 1 has only 2 operating scientific instruments remaining, its magnetometer and plasma wave system. Voyager 2 still has 3, including those same 2 instruments, along with its cosmic ray detector. The cameras that once photographed the planets were shut down in 1989 and 1990. The spacecraft no longer observe space in a way that human eyes can easily understand, yet they continue to sense invisible phenomena. The magnetometer records the direction and strength of the magnetic field surrounding the spacecraft, while the plasma wave system listens for electrical oscillations in the environment. Voyager has gradually lost many of its original senses, but those that remain are especially well suited to the region of space through which it now travels. The fragility of this communication is not caused by distance alone. Voyager needs electricity to operate its computers, radio transmitter, scientific instruments, and the heaters that prevent critical components from becoming too cold. It also requires fuel for the small thrusters that control its orientation. If power falls too low, if the transmitter malfunctions, if a fuel line freezes, or if the spacecraft turns away and cannot correct itself, the signal may disappear. Voyager would not necessarily have been destroyed. It could continue traveling, but from Earth, it would be like someone walking into a dark room and closing the door behind them. There have been moments when that possibility came very close. A single change in the transmission system or a small shift in antenna alignment can be enough to prevent the Deep Space Network from hearing the spacecraft in the usual way. When this happens, the Voyager team must examine transmission modes designed decades ago and send commands whose results cannot be known until many hours later. No repair can be performed directly. Every solution must travel through the same fragile communication link that is already experiencing trouble. The fact that both Voyagers remain in contact is not the result of an immortal machine, but of redundant design, generations of engineers, and thousands of small decisions. Perhaps the most remarkable thing is not how far Voyager has traveled, but that humanity can still hear it at all. Between Earth and the spacecraft, there are no cables, relay satellites, or stations waiting along the way. A transmitter built in the 1970s sends out an extraordinarily faint signal. Nearly a day later, that signal reaches a receiving dish on Earth, where it is amplified, decoded, and transformed into numbers that scientists can read. Then another command is sent back into the darkness. The conversation continues this way, so slowly that every question requires patience, yet with enough persistence to endure across generations of human lives. Voyager 1 and Voyager 2 show that immense distance does not necessarily mean absolute silence. As long as the spacecraft have enough electricity to transmit, enough fuel to maintain their orientation, and antennas on Earth that can still recognize their voices, the thread of communication remains unbroken. Yet, with every passing year, The signals must travel farther, the available power grows smaller, and the decisions facing the mission team become more difficult. The fact that Voyager answers today does not guarantee that it will answer forever. That uncertainty makes every returning stream of data feel like a quiet confirmation that, on the far side of the darkness, the spacecraft are still continuing their journey. But to understand how these two small machines could travel so far without carrying an enormous supply of fuel, we must return to the summer of 1977. At that time, Jupiter, Saturn, Uranus, and Neptune were approaching a rare arrangement, opening a path that engineers would have to wait nearly 2 centuries to encounter again. Voyager did not carry enough fuel to fly on its own from Jupiter to Saturn, then Uranus, and finally Neptune. If the spacecraft had needed to burn its engines continuously to cross each of those immense distances, it would have required a fuel supply so large that launching it from Earth would have been nearly impossible. Voyager's journey therefore depended on more than the power of its rocket. It needed to borrow momentum from the planets themselves in order to travel farther. In the late 1970s, the 4 giant planets of the solar system were approaching a rare arrangement. Jupiter, Saturn, Uranus, and Neptune were not aligned in a perfectly straight line, but their relative positions allowed a spacecraft to travel from one planet to the next through a sequence of carefully planned encounters. Such a favorable opportunity appears only about once every 176 years. If humanity had missed it, many generations would have passed before a similar path became available again. That arrangement did not automatically create an easy route. The planets were still separated by hundreds of millions, and sometimes billions, of kilometers. Each world traveled around the Sun at its own speed, along its own orbit, and none of them would remain still while the spacecraft approached. Engineers had to calculate not only where a planet was at the time, but where it would be many months or even years later. Voyager had to be launched toward the place where the planet would eventually appear, much like throwing a ball ahead of a moving target so that the two arrive at the same point. A small error at the beginning could grow into an enormous distance after the spacecraft had traveled hundreds of millions of kilometers. If Voyager reached Jupiter even slightly too early or too late, its approach angle would change. Once that angle changed, the path towards Saturn would no longer unfold as planned. And if the spacecraft missed Saturn, the entire journey toward the more distant worlds might come to an end. Before the 2 Voyagers left Earth, engineers therefore studied thousands of possible trajectories, comparing travel times, encounter distances, safety margins, and the scientific targets each route could observe. The key to the journey was a technique known as a gravity assist. The name may suggest that a planet simply pulls a spacecraft forward with its gravity and then releases it. But what actually happens is more subtle. Imagine stepping onto a moving walkway. You did not create the motion of the walkway, but by stepping onto it at the right moment and from the right direction, you can be carried forward more quickly without running the entire distance yourself. Voyager did something similar with a planet moving around the Sunday. As the spacecraft approached Jupiter, the planet's immense gravity curved its path. If Jupiter had been motionless in space, Voyager would have accelerated as it drew closer, then lost nearly the same amount of speed as it moved away. But Jupiter was not standing still. It was traveling along its orbit around the Sunday. By passing along the correct side of the planet, Voyager could take a tiny portion of Jupiter's orbital momentum and depart at a greater speed than it had before the encounter. That energy did not appear from nowhere. In principle, the planet lost an extremely small amount of its own momentum. Jupiter, however, was so much more massive than Voyager that the change was almost impossible to detect. For the planet, the difference was far too small to have any practical meaning, but for a spacecraft weighing less than a metric ton, the energy it gained was enough to alter its trajectory and shorten the journey by many years. A gravity assist is not a single push that works equally in every direction. The result depends on the spacecraft's speed, its distance from the planet, and the angle at which it passes. Approaching from one direction may cause Voyager to accelerate. Passing from another may slow it down or redirect it onto a different orbit. Engineers therefore used each planet not merely as a place to gain speed, but as an enormous gravitational curve that could reshape both the spacecraft's velocity and its direction. This also meant that the mission could not freely change its plans after every encounter. Once Voyager flew past a planet, its new trajectory had already been partly determined. A close pass by a moon might provide priceless images, but it could also pull the spacecraft away from the route toward its next destination. On a journey this long, every scientific choice carried a cost. Voyager could not closely observe every world and still preserve its original path. Voyager 2 was launched first, on the 20th of August 1977. Voyager 1 left Earth 16 days later, on September 5. Their names, however, were not based on launch order. Voyager 1 was placed on a faster, shorter trajectory toward Jupiter and Saturn, allowing it to reach the first two planets before Voyager 2. Voyager 2 followed a slower route, but that path preserved its opportunity to continue onward to Uranus and Neptune. The two spacecraft were nearly identical in structure, but they were not simply a primary spacecraft and a backup. They were sent along separate routes with different objectives. Voyager 1 prioritized important encounters at Jupiter and Saturn, especially a close approach to Titan, Saturn's largest moon. Voyager 2 followed a more flexible path, allowing it to continue deeper into the outer solar system if the early stages succeeded and the spacecraft remained capable of operating. When the Voyagers left Earth, their original mission focused mainly on Jupiter and Saturn. Reaching Uranus and Neptune was not yet a firm promise. Those worlds were too distant, the travel time was too long, and no one knew whether a spacecraft built in the 1970s could survive for more than a decade in space. Only after Voyager 2 completed its first encounters, remained in communication, and continued operating properly, was the mission extended. What makes that survival so remarkable is that Voyager was not an enormous machine. Its most prominent feature was the dish-shaped antenna used to communicate with Earth. A long boom extended from the spacecraft's body, carrying the magnetometer far enough away to protect its measurements from electromagnetic interference produced by Voyager itself. Other instruments measured charged particles, cosmic rays, plasma, and the surrounding environment. During the planetary encounters, its cameras served as Voyager's eyes, returning images unlike anything humanity had ever seen. Inside the spacecraft were control computers with extremely limited capabilities compared with modern devices. But they did not need to process video, run social networks, or manage thousands of applications at once. They were designed to perform a small number of clearly defined tasks: monitor the condition of the spacecraft, receive commands from Earth, control the instruments, and keep Voyager properly oriented in space. That simplicity, combined with built-in redundancy, helped the spacecraft continue operating far beyond their expected lifetimes. Another challenge was power. Near Earth, many spacecraft rely on solar panels, but sunlight grows weaker with distance. At Jupiter, the amount of sunlight available is already far lower than it is near Earth. At Neptune, sunlight is reduced to only a tiny fraction of that level. If Voyager had depended entirely on solar panels, it would have required an enormous light-collecting surface and still might not have produced enough electricity to operate its instruments. Instead, each Voyager carries 3 radioisotope thermoelectric generators. Inside them is plutonium-238, a material that naturally releases heat as it decays. Voyager does not burn plutonium as fuel, nor does it carry an active nuclear reactor. A portion of the naturally produced heat is converted into electricity, allowing the spacecraft to operate even when sunlight has grown too faint. This power source will not last forever. Both the heat output and the ability to convert it into electricity gradually decline over time, but the decrease is slow enough for Voyager to pass the giant planets and continue operating for decades. As power becomes more limited, engineers shut down systems that are no longer essential, one by one. Much like a house on a winter night, preserving light and warmth only in its most important rooms, Voyager also does not need to keep its engines running in order to continue traveling. In space, where there is almost no resistance, an object already in motion will remain in motion. The spacecraft's small thrusters are used mainly to adjust its trajectory when necessary and to keep its antenna pointed toward Earth. Most of the journey is a long, silent coast shaped by the initial launch, the gravitational assists, and a series of carefully calculated corrections. Voyager can be imagined as a very small boat moving through an immense system of currents. It cannot create every current on its own, but if the navigator understands their flow and chooses the right moment, the boat can travel far beyond what its own power would normally allow. For Voyager, those currents are the orbital motion and gravity of the planets. Yet nature did not prepare everything in advance. The planetary arrangement only created the possibility. Humanity still had to recognize it, build a spacecraft durable enough to survive, calculate the route with extraordinary precision, and launch within a very narrow window. If the rocket had failed, if a critical computer had stopped working, or if the spacecraft had arrived at the wrong position, that once in 176 years, opportunity might have passed without producing anything at all. Voyager was therefore more than an achievement of engines, computers, or materials. It was the result of planning many years beyond the beginning of the mission. Its designers had to imagine where the spacecraft would be in the future, when many of them might already have retired and a new generation of engineers would have taken over. Some of the commands later sent to Voyager were written by people who had never stood in the room where the spacecraft was built. The rare doorway in the sky opened in 1977, and the two Voyagers passed through before it closed. But at the time, no one could know with certainty what lay ahead. Jupiter was still a world observed from a distance through telescopes. Its moons were often imagined as cold, nearly motionless bodies of rock and ice suspended in the darkness. Then Voyager drew close to the giant planet. In the first images sent home, the clouds began to reveal themselves as intricate streams of motion. A faint ring system slowly emerged, and a strange detail appeared near the edge of the moon Io. The doorway had opened. The first destination was a world where Voyager was about to discover that a small moon could be more violent than many planets. Before Voyager, distant moons were often imagined as little more than cold bodies of rock or ice, barely changing in the darkness. They orbited giant planets, received very little sunlight, and seemed to lack enough energy to produce any major activity. But when Voyager reached Jupiter in 1979, that picture began to fall apart. One of the planet's small moons was anything but quiet. Its surface was constantly being torn open, hot material was erupting into space, and the entire world seemed to be burning from within. Voyager 1 approached Jupiter in March 1979, after a journey of about a year and a half. A few months later, Voyager 2 flew past the planet as well. When the first images arrived, Jupiter was no longer just a bright disk crossed by a few colored bands. As it appeared through telescopes, it emerged as an immense world in constant motion, with cloud belts stretching around the planet, swirling masses of gas folding into one another, and storms larger than Earth. Jupiter has no clearly defined solid surface where a person could stand, as they might on Earth or the Moon. A spacecraft descending deeper would encounter layers of gas that became progressively denser, hotter, and more intensely pressurized. There is no sharp boundary where the atmosphere ends and the ground begins. What Voyager saw from above was mainly a succession of cloud layers surrounding a world composed mostly of hydrogen and helium. The light and dark bands across Jupiter are not regions of differently colored land. They are atmospheric currents moving at different speeds and in different directions. Between them lie countless circular vortices, smaller storms, and intricate structures. Voyager revealed that Jupiter's atmosphere was not simply divided into a few orderly stripes. It resembled an ocean without a surface, where enormous streams of gas collided, twisted together, and continually changed shape. The most prominent feature was the Great Red Spot, a storm system that people on Earth had observed for centuries. Through Voyager's cameras, it appeared as a vast atmospheric vortex, with layers of clouds circling its center. The Great Red Spot is not an object fixed to a surface, because Jupiter has no solid surface of that kind. It is a long-lived storm within the atmosphere, sustained by the movement of powerful currents and by energy rising from the planet's interior. Voyager also detected lightning in Jupiter's atmosphere. This showed that electrical processes were taking place inside the thick clouds, fundamentally similar to those found in thunderstorms on Earth, though the scale, composition, and conditions were entirely different. Radio signals and images taken on the planet's night side helped scientists recognize flashes within the clouds, Jupiter was therefore not merely an enormous sphere of gas, but a world of intensely active weather. Another discovery was hidden in a place far more difficult to see. Voyager observed a thin, dark ring surrounding Jupiter. Before then, Saturn was famous for its bright and obvious rings, while Jupiter was not considered to have a significant ring system. But images taken with the light shining from behind revealed a faint layer of material encircling the planet. Jupiter's rings are difficult to see from Earth because they are extremely thin, dark, and reflect very little light. Most of their material consists of tiny dust particles, unlike the bright pieces of ice found in Saturn's rings. Under ordinary viewing conditions, the brilliance of Jupiter itself easily overwhelms them. Voyager was able to detect the rings because it came much closer and observed them under favorable lighting, much like dust in a room, becoming visible only when a beam of sunlight shines through it from behind. Yet, the clouds, lightning, and faint rings were still not the greatest surprise. The discovery that profoundly changed humanity's view of distant moons began with an image of Io. While examining a photograph of the moon, a member of the navigation team noticed a strange structure rising above the horizon. It looked like a hazy umbrella or a large cloud suspended over the surface. At first, the feature might have been dismissed as an imaging error, scattered light, or some unrelated detail. But when scientists examined it more carefully, they realized that it was a plume of material erupting from Io. The material was being thrown hundreds of kilometers above the surface before falling back down. It was the first time humanity had ever observed an active volcano on another world beyond Earth. When Voyager 2 passed by several months later, it also recorded ongoing volcanic activity. Some plumes were still present, others had changed, and new regions had appeared. This proved that Io had not merely been active in the distant past. Geological processes were unfolding during the very months in which the two spacecraft were watching. Io's surface looked nothing like the familiar face of Earth's moon. It was not gray, nor was it covered with many obvious impact craters. Instead, complex patches of yellow, orange, red, white, and black spread across the landscape. These colors were associated with sulfur and sulfur compounds that had erupted, frozen, and then been buried beneath fresh deposits. Io's surface was being continually renewed, erasing many of the older scars left by impacts. But this raised a major question. Io lies much farther from the sun than Earth. Sunlight there is weaker, and the moon is not large enough to retain internal heat in the same way as a giant planet. What source of energy could sustain volcanic activity so intense? The answer lies in gravity, though not in Jupiter's gravity alone. Io can be imagined as a soft ball being gently squeezed again and again. As it orbits Jupiter, the planet's enormous gravitational pull acts more strongly on the side facing Jupiter than on the side farther away. If Io's orbit were a perfect circle, the amount of deformation would remain relatively constant. But neighboring moons such as Europa and Ganymede continually influence Io's orbit, causing its distance from Jupiter to change slightly over time. As Io moves closer, the gravitational pull becomes stronger. As it moves farther away, the pull weakens. This repeating variation causes the entire moon to flex and compress continuously. Solid rock does not deform easily, so the process generates friction and heat within Io. Over millions of years, that heat has been sufficient to melt material, sustain lakes of lava, and power violent eruptions. This process is known as tidal heating. The name is related to the tides on Earth, where the moon's gravity causes ocean levels to rise and fall. On Io, however, gravity does not merely move an ocean. It distorts nearly the entire moon. Instead of producing rising and falling water, it generates heat inside the rock. The significance of this discovery extended far beyond Io itself. Before then, when scientists considered whether a world might remain geologically active, they often focused on heat received from the sun or heat left over from its formation. Io revealed that another source of energy could exist. Even a small moon far from the sun could become hot and violent if gravity continually flexed its interior. Voyager then drew attention to Europa, another of Jupiter's moons. While Io appeared colorful and scarred by volcanic activity, Europa looked bright, smooth, and covered in ice. Long, dark lines crossed its surface, intersecting in an intricate network. Compared with many other moons, Europa had very few large impact craters. Impact craters can be thought of as a record of a surface's age. A region that remains unchanged for a long time will usually accumulate more craters because small asteroids and other objects continue to strike it over millions or billions of years. If a surface has relatively few craters, it may be geologically young or may have been renewed by some ongoing process. Voyager's images therefore suggested that Europa's surface was not entirely motionless. The fractures may have been connected to the icy shell being stretched, pulled apart, and shifted. Some regions appeared to have broken apart and then frozen again. Voyager, however, could provide only images of limited resolution and could not look directly through the ice. The idea of a liquid water ocean beneath Europa was strengthened much more by later missions and measurements. Voyager helped open the question, but it did not by itself fully prove that a deep ocean definitely existed. This distinction is important. The fractures, the young surface, and the effects of tidal forces form a picture consistent with water beneath the ice, but there remains a significant scientific distance between interpreting surface images and determining the complete structure of a moon's interior. That distance between evidence and certainty is precisely what gives Voyager its value. A mission does not have to answer every question in order to transform science. Sometimes its most important contribution is revealing that the old question was no longer the right one. Before Voyager, scientists might have asked just how cold and motionless distant moons could be. After Io and Europa, the question became something entirely different. How many moons are being warmed by gravity, resurfaced from within, or concealing environments that have never been seen? Ganymede and Callisto also revealed landscapes of their own. Ganymede displayed bright and dark regions, long grooves, and signs that its surface had passed through several periods of change. Callisto, by contrast, was densely covered in impact craters, like an archive preserving the ancient history of the solar system. Jupiter's 4 largest moons were no longer 4 similar points of light. Each world had its own history, structure, and level of activity. Voyager therefore returned more than beautiful images of Jupiter. It transformed a system once viewed as a single planet surrounded by a few small moons into a collection of profoundly different worlds. One was violently volcanic, another was covered in ice and might conceal an ocean. Another possessed a complex landscape, while the last preserved an ancient surface crowded with impact craters. The discovery at Io also changed the way scientists searched for environments capable of sustaining geological activity. Distance from the sun was no longer the only factor that mattered. A world could remain cold at its surface, while preserving internal heat through tidal forces. This expanded the range of places worth studying, not only within the solar system, but also around planets orbiting other stars. As the 2 Voyagers moved away from Jupiter, the giant planet slowly diminished behind them. The plumes on Io continued to rise, even though the spacecraft's cameras were no longer there to watch. Europa kept its secrets beneath the ice. The faint ring system continued circling through the dim sunlight, while the great red spot kept turning among Jupiter's powerful atmospheric currents. Voyager arrived with the idea that moons were cold and lifeless bodies of rock. It departed with evidence that a small moon could become one of the most violently active worlds in the solar system. But Saturn was waiting ahead, where rings that seemed almost perfect were about to reveal themselves as a system filled with gaps, waves, knots, and motion unlike anything humanity had ever seen clearly before. From a distance, Saturn's rings look like perfect circles, arranged neatly around a pale yellow planet. Through telescopes on Earth, they appear thin, bright, and almost motionless, as though someone had drawn a series of symmetrical lines around the giant world. But as Voyager moved closer, that perfection began to break apart. The rings were not continuous at all. They contained countless gaps, waves, dark streaks, and structures so small that humanity had never been able to see them clearly before. Voyager 1 reached Saturn in November 1980, while Voyager 2 flew past the planet in August 1981. The 2 encounters occurred less than a year apart, yet they provided different perspectives on the same system. When the images arrived, scientists realized that Saturn's rings were not a solid disk. If someone could somehow step onto them, there would be no continuous surface on which to stand. Instead, The rings were made of countless particles of ice, rock, and dust, ranging from grains as small as sand to objects larger than a house, all traveling around the planet together. Each particle in the rings behaves like a tiny moon. It follows its own orbit, obeys Saturn's gravity, and continually interacts with the particles around it. Those closer to the planet move faster, while those farther away travel more slowly. The rings, therefore, do not rotate like a rigid disk. Different regions slide past one another, collide gently, gather together, and separate again, creating a system that is always changing even though it appears peaceful from afar. Voyager revealed that thousands of smaller ringlets existed between the major rings. Dark lines that seemed like completely empty gaps sometimes still contained faint material. Bright regions that appeared uniform were divided into narrow bands with different densities. The closer scientists looked, the more the rings resembled a composition made from countless rhythms of motion, with each particle of ice playing a tiny part, while the entire system remained connected through gravity. Some small moons play an important role in preserving the structure of the rings. They are often called shepherd moons because their gravity can pull on ring particles, prevent a narrow ring from spreading too far, or create relatively sharp edges. The image is similar to shepherds keeping a flock from scattering, though no deliberate guidance is taking place here. Everything happens naturally through orbital motion and gravitational forces. When a moon travels near the edge of a ring, it exerts a slight pull on the icy particles each time it passes. A single interaction is almost insignificant, but when repeated thousands or millions of times, it can create a clearly defined boundary, a long wave, or a gap within the rings. This shows how large structures can sometimes emerge from small but persistent forces acting over immense periods of time. Voyager also observed shapes that were more difficult to explain. Within the F-ring, material appeared to twist, braid, or gather into bright knots. Some of these structures changed within a short period of time. The F-ring lies close to small moons whose gravity continually disturbs its material, preventing it from maintaining a stable shape. What Voyager saw was not a peaceful circle, but a region of matter being constantly pulled, compressed, and rearranged. Another surprise was the appearance of dark spokes across the B-ring. They looked like faint streaks extending in an almost radial direction, unlike the usual circular patterns. These spokes were not permanent gaps. They appeared, changed, and disappeared, suggesting that tiny dust particles might be lifted above the ring plane or influenced by electrical charges and Saturn's magnetic field. Voyager could not fully explain the mechanism, but its images proved that gravity was not the only force affecting the rings. Electrical and magnetic phenomena could also contribute to their subtle changes. These details transformed the way humanity viewed Saturn. The rings were no longer merely a perfect decoration surrounding the planet. They were a physically active environment where material moved, collided, responded to moons, and changed over time. Their stillness existed only when seen from very far away. Beyond the rings were moons with completely different sizes, colors, and histories. One of them was Enceladus, a small moon with a surface so bright that it reflected most of the sunlight falling upon it. Voyager did not see the plumes of water vapor and ice erupting from the South Polar region as the Cassini spacecraft would many years later. Its images did reveal, however, that Enceladus was not a completely motionless body of ancient ice. Some regions of Enceladus had very few impact craters, while others appeared much older. Its surface contained fractures, grooves, and areas that seemed to have been altered in the past. This suggested that some process had renewed parts of the surface. Voyager could not determine exactly what that process was. It did not see a subsurface ocean, directly measure any plumes, or confirm that liquid water existed beneath the ice. But it left behind a question large enough for later missions to continue investigating. Many years later, Cassini flew past Enceladus and discovered plumes of material erupting from fractures near the South Pole. Within those icy particles were traces of water, salts, and other compounds, providing strong evidence for an ocean beneath the moon's frozen crust. Voyager did not uncover the entire answer on its own, but its early images showed that Enceladus deserved a closer look. This is one of the ways science advances. One spacecraft notices something unusual, the next moves closer, and each generation adds another piece to the picture. While Enceladus offered subtle clues, Titan appeared as a world no one could see through. It is Saturn's largest moon and is even larger than the planet Mercury. Before Voyager, scientists already knew that Titan had an atmosphere, but they did not know how thick it was or what it was primarily made of. As Voyager approached, its cameras could not see mountains, plains, or impact craters. The entire surface was hidden beneath a dense orange haze. Titan's atmosphere consists mostly of nitrogen, just as nitrogen is the main component of Earth's atmosphere. But conditions on the two worlds are very different. Titan is far colder and contains methane along with organic compounds formed in the atmosphere. Sunlight acts upon the methane, driving complex chemical reactions that produce tiny suspended particles. Those particles create the orange haze that conceals the surface. Visible light cannot easily pass through that veil. Voyager could measure the atmosphere, observe the hazy layers surrounding Titan, and collect data on its temperature, pressure, and composition. But its cameras could not clearly see what lay below. In the images, Titan appeared as an almost featureless orange sphere. That concealment only made the moon more intriguing. If a world possessed such a thick atmosphere and such complex chemistry, what might be happening beneath the clouds? Voyager 1 was placed on a special trajectory that brought it close to Titan. The moon was such an important scientific target that the spacecraft's path was designed around this encounter. Engineers wanted to use Titan's gravity to alter Voyager's trajectory while gathering the most detailed atmospheric data possible. But every gravity assist changes the spacecraft's future. After passing Titan, Voyager 1 was deflected upward, away from the plane in which most of the planets orbit the Sunday. It was no longer on a suitable path toward Uranus and Neptune. The decision to approach Titan produced invaluable data, but it also ended Voyager 1's opportunity to visit the two more distant planets. This was not a mistake. It was a choice calculated in advance. Titan was one of the most compelling worlds around Saturn, and no one knew whether Voyager 2 would remain operational long enough to complete the rest of the journey. If both spacecraft had followed the same trajectory and encountered the same problem, humanity might have lost the entire opportunity. By dividing the mission, one spacecraft could focus on Titan, while the other preserved the possibility of continuing outward. Voyager 2 passed Saturn along a different path. Its gravity assist there kept it within a favorable plane for traveling toward Uranus. Yet the continuation of the journey was not automatic. Engineers still had to examine the condition of its instruments, its power supply, its communication system, and its trajectory before deciding to extend the mission. Uranus was still many years away, and no one could make repairs if a critical component failed along the way. The moment the two Voyagers departed Saturn was also the moment their journey truly divided into two separate stories. Voyager 1 left the planetary plane and began following a path that would carry it beyond the heliosphere sooner. It would never again pass close to another major planet. Ahead lay increasingly empty space, where photographic targets gradually disappeared, and the spacecraft's mission shifted from planetary observation to studying the environment far from the Sunday. Voyager 2 continued along the longer route. It became humanity's only hope of seeing Uranus and Neptune at close range. The two spacecraft had been built almost identically, launched only 16 days apart, and had both flown past Jupiter and Saturn. But after Titan, they were no longer companions in any orbital sense. Each headed toward a different region of the sky, and the distance between them continued to grow. This separation reveals how rarely space missions can accomplish every possible goal. Every second of observation, every close encounter with a moon, and every angle of approach forces engineers to make a choice. Flying close to Titan might mean losing the opportunity to reach Neptune. Preserving a route toward Uranus might mean observing Titan from a less favorable distance. Science is not simply the effort to collect as much data as possible. It is also the art of deciding which questions deserve priority when time, fuel, and trajectory are all limited. Saturn therefore became a major turning point in the journey. Voyager arrived with the goal of observing the planet, its rings, and its moons. It departed with a new picture of rings in constant motion, small moons capable of shaping the material around the planet, an icy moon showing signs of geological change, and an orange world concealing its surface beneath a dense atmosphere. Behind the two spacecraft, Saturn's rings continued to turn. Individual particles of ice followed their own orbits. Shepherd moons maintained narrow edges. Dark spokes appeared and faded, and Titan kept its surface hidden beneath the haze. Voyager 1 carried its data about Titan, away from the path of the planets. Voyager 2 continued deeper into the outer solar system, where sunlight grew steadily weaker and the worlds ahead had never been seen at close range by any spacecraft. 5 years later, Voyager 2 reached a pale blue planet rotating almost completely on its side. Beside it was Miranda, a moon whose surface looked as though it had been torn into separate pieces and reassembled in an order scientists had never imagined. Voyager 2 had only a few hours to observe Uranus at close range, yet what it saw during that brief encounter would make up most of humanity's direct knowledge of the planet for decades. Before then, Uranus had appeared through telescopes as little more than a small, pale blue point of light. After the 24th of January 1986, it became a world with dark rings, moons shaped by different geological histories, and a magnetic field unlike anything scientists had expected. Yet, among everything Voyager discovered, the strangest sight was not found on the giant planet itself, but on Miranda, a small moon whose surface looked as though it had been assembled from pieces of several unrelated worlds. After leaving Saturn, Voyager 2 traveled for another 4.5 years before reaching Uranus. During that time, sunlight grew steadily weaker, while signals between the spacecraft and Earth took several hours to travel in either direction. When distant observations began in late 1985, Voyager was entering an environment where sunlight was nearly 400 times weaker than it is near Earth. This made photography far more difficult. The cameras needed longer exposures to gather enough light, but the spacecraft was still moving at tremendous speed, so even a slight vibration or pointing error could blur surface details into streaks. The mission team had to carefully calculate how to rotate the spacecraft and keep each target within view long enough for the cameras to capture usable images. As Uranus grew larger in the frame, it appeared as a pale blue sphere with almost none of the clearly defined cloud bands seen on Jupiter or the prominent storms that would later be observed on Neptune. That blue color did not mean the planet was covered by an exposed ocean. Methane in the atmosphere absorbs some of the red light and allows more green and blue light to return to space. As a result, the planet appears softly blue to human eyes, even though there is no ocean surface beneath the atmosphere where a spacecraft could land. Uranus is known as an ice giant, but the word ice should not suggest a frozen solid sphere. The planet has no true surface like Earth. Its upper atmosphere is composed mainly of hydrogen and helium, along with a smaller amount of methane. Deeper below, pressure and temperature rise until water, ammonia, and methane may exist in hot, dense states, very different from the familiar liquids or ices found on Earth. A spacecraft attempting to descend would never find solid ground on which to land. It would continue sinking into progressively denser layers until the pressure and heat destroyed it. What makes Uranus even more unusual is the way it rotates. The planet's axis is tilted by nearly 98 degrees relative to the plane of its orbit. Most planets can be imagined as slightly tilted spinning tops moving around the Sun, while Uranus resembles a sphere lying almost on its side and rolling along its path. When Voyager 2 arrived, one of the planet's polar regions was pointed almost directly toward the Sunday. Its moons and rings also appeared arranged around it like circles viewed nearly face-on, making the encounter resemble a spacecraft flying toward the center of an enormous target. This extreme tilt creates seasons unlike anything on Earth. Uranus takes about 84 years to complete one orbit around the Sun, so each season can last more than 2 decades. During one part of its orbit, one pole remains continuously directed toward the Sun, while the opposite pole endures a prolonged darkness. Many years later, the situation gradually reverses. Voyager observed the planet at only one particular moment in this very long seasonal cycle. The nearly featureless images it returned did not necessarily mean Uranus was always so inactive. Telescope observations made many years later revealed more distinct clouds and atmospheric changes as the seasons shifted. Voyager 2 had very little time for close observation. The geometry of its flight path had to allow the spacecraft to gather data about Uranus while also preserving the trajectory that would carry it onward to Neptune. Had it followed a different route to observe the planet longer or approach another target more favorably, Voyager might have lost the path ahead. As a result, the period of closest study lasted only about 5.5 hours. During those few hours, the cameras and instruments had to observe the planet, its rings, its magnetic field, and its major moons in sequence, all while the spacecraft raced through the Uranian system at tens of thousands of kilometers per hour. Voyager discovered 10 previously unknown moons and 2 new rings, in addition to those already known. Unlike Saturn's bright rings of ice, the rings of Uranus were narrow, dark, and difficult to observe. Some varied noticeably in thickness and in how much light they blocked, showing that their material was not evenly distributed. Small moons near the rings may help confine the particles into narrow bands, much like the shepherd moons around Saturn. Voyager had only one opportunity to pass through the system, but those brief measurements were enough to reveal that the rings of Uranus were far more complex than a few dark circles surrounding the planet. The planet's magnetic field produced an even greater surprise. On Earth, the magnetic axis does not perfectly align with the rotational axis, but the two remain relatively close. At Uranus, Voyager measured a magnetic axis tilted by nearly 59 degrees from the axis of rotation, while the center of the magnetic field was displaced from the center of the planet by roughly 1/3 of its radius. If the field could be seen with the naked eye, it would not surround Uranus in a balanced, symmetrical shape. As the planet rotated, the magnetic structure swept through space in a complex motion, like a lamp with an off-center beam attached to a rolling sphere. This measurement suggested that Uranus's magnetic field might not be generated deep near the core in the simple way scientists had often imagined. Instead, it may arise within electrically conductive layers, located higher up and distributed unevenly inside the planet. Voyager, however, measured the field only while passing through one region at one particular time. A single flyby could not reveal how the magnetic field changed across multiple seasons or determine the planet's exact internal structure. Uranus therefore became clearer in some ways while opening questions that still have not been fully resolved. Yet the most striking images from the encounter did not come from the pale blue planet. As Voyager passed close to Miranda, its cameras began recording a moon only about 500 kilometers across. At such a small size, Miranda had been expected to be a cold, ancient world covered in impact craters. Small bodies usually lose their internal heat quickly, making it difficult for them to sustain geological activity for long periods. But the images appearing on the screens revealed a surface stranger than almost anything Voyager had encountered before. Miranda contained heavily cratered regions, lying directly beside bright and dark bands, ridges, valleys, fault cliffs, and large oval areas, known as coronae. The boundaries between some regions were so distinct that they looked like separate pieces of terrain placed beside one another without fully fitting together. NASA once compared its appearance to a body assembled from mismatched parts. Yet the patchwork visible on Miranda does not necessarily mean the moon was literally shattered into pieces and then reassembled. Instead, it shows that the surface experienced many different geological processes at different times. Part of Miranda's surface is ancient, rugged, and heavily cratered. Other regions contain fewer craters, along with bright and dark bands, ridges, and valleys arranged in large patterns. The number of impact craters helps scientists estimate the relative age of a surface. A region that remains unchanged for a long time usually accumulates more craters. An area with fewer craters may be younger or may have been resurfaced, erasing older impact scars. On Miranda, old and young terrain lie side by side, showing that the moon's history did not unfold during a single period. Miranda's fault scarps are especially deep. Some canyons are several times deeper than the Grand Canyon. In the moon's weak gravity, a rock falling from the top of the highest cliff might take several minutes to reach the bottom. High-resolution images reveal ridges that have been cut apart, blocks of terrain that have shifted, and surfaces showing signs of compression or stretching. This is not the landscape of a completely motionless body of ice. At least in the past, Miranda's crust was severely deformed. The source of energy that created these landforms remains uncertain. Miranda is too small to have easily preserved much of its original heat from the time of its formation until today. One possibility is that its orbit was once disturbed by other moons of Uranus. If Miranda entered an orbital resonance in the past, changing gravitational forces may have repeatedly flexed and compressed its interior, producing tidal heating similar to the mechanism that warms Io, though with different intensity and results. That heat may have softened some of the ice within the moon, allowing material to move, the surface to stretch, and the coronae to form. Another idea once proposed is that Miranda may have experienced major impacts that altered or disrupted part of its structure. In popular descriptions, the moon is sometimes portrayed as having exploded and then reassembled itself. But Voyager's images are not sufficient to confirm that story. A major collision, tidal heating, movement of interior ice, and several periods of geological restructuring may all have contributed to the surface seen today. Scientists must use models, crater counts, and the shapes of the terrain to test each possibility, but they have no data from seismometers, ice-penetrating radar, or a long-term orbiter. The greatest limitation came from Voyager's flight path itself. The spacecraft passed Miranda only once and observed mainly one part of the moon under the lighting conditions of 1986. Regions in darkness or on the less favorable side were not photographed clearly. The famous mosaics of Miranda were assembled from several frames, combining data at different resolutions to fill in the gaps. They reveal an astonishing landscape, but they are not a complete map of the entire moon. This is the difference between a flyby and an orbital mission. Voyager could observe only what passed in front of its instruments during a brief period of time. It could not return during another season, view the same location under different lighting, or monitor changes over many years. An orbiter could make hundreds of passes, create a global map, and adjust its plans in response to new discoveries. Voyager had to gather everything it could and then continue onward with no second opportunity. Even so, the value of the flyby did not depend on answering every question. In just a few hours, Voyager transformed Uranus from a distant point of light into a system containing an ice giant, dark rings, an off-center magnetic field, and moons, shaped by different geological histories. Miranda changed from a tiny point of light into evidence that even a modestly sized world could experience violent transformation. The images did not fully explain the moon's past, but they showed that the earlier, simpler models were no longer enough. As Voyager 2 moved away from Uranus, the pale blue planet slowly diminished behind it. No spacecraft remained to watch the seasons change, the magnetic field sweep through space, or the unseen regions of Miranda's surface. Nearly 4 decades later, Voyager 2 remains the only spacecraft ever to have visited the Uranian system at close range. The data collected during those few hours continue to shape questions about the structure of ice giants and the histories of distant moons. But Voyager 2's journey was not yet over. Ahead lay another 3 years of travel through a region where sunlight continued to fade. At the end of the planetary path waited Neptune, a deep blue world where clouds moved at astonishing speeds. Faint rings nearly vanished into the darkness, and a frozen moon still sent material erupting into space. Neptune receives hundreds of times less sunlight than Earth, yet its atmosphere is anything but still. More than 4 billion kilometers from the Sun, where daylight has faded into a cold, pale blue glow, clouds still race at tremendous speeds. Storm systems continue to form and change, and winds can far exceed anything ever measured on Earth. When Voyager 2 approached in 1989, the final planet of the Grand Tour did not appear to be a world that had fallen asleep. It emerged as a powerful atmospheric machine, still operating deep within the darkest region of the solar system. Voyager 2 had been traveling for nearly 12 years since leaving Earth. It had passed Jupiter, Saturn, and Uranus, enduring radiation, extreme cold, trajectory corrections, and thousands of hours of operation without any possibility of direct repair. After flying past Uranus in 1986, the spacecraft carried out a major course correction toward Neptune. Every deviation had to be addressed far in advance, because once Voyager reached the planet, it would pass too quickly to turn back. On August 25, 1989, Voyager 2 flew about 4,800 kilometers above Neptune's cloud tops, closer than it had come to any planet during its journey. It was the first spacecraft, and remains the only one, ever to visit Neptune at close range. From Earth, Neptune is too distant to be seen with the naked eye. Even through telescopes, it once appeared only as a small blue disk, with too little detail to reveal what was happening in its atmosphere. Voyager began observing the planet from afar several months before the encounter, taking repeated images to track changes in clouds and storms as Neptune rotated. As the spacecraft moved closer, dark regions, bright clouds, and atmospheric bands became increasingly visible, revealing that beneath the seemingly uniform blue color was a world in constant motion. One of the most famous features in the images was a large, dark region in the southern hemisphere known as the Great Dark Spot. Nearly the size of Earth, it appeared to be an enormous storm system. Around it stretched bright clouds that may have occupied higher layers of the atmosphere, forming as rising air cooled and caused methane to freeze into tiny crystals. Voyager also observed a smaller dark region and a rapidly moving bright cloud that the science team nicknamed the Scooter because it seemed to race around the planet in a steady rhythm. These features made Neptune an immediately recognizable paradox. The planet lies about 30 times farther from the Sun than Earth. Sunlight there is so weak that, judging only by the energy received from outside, one might expect the atmosphere to be sluggish and nearly frozen. Yet Voyager measured winds exceeding 1,000 kilometers per hour, with some regions moving far faster. To understand this, it is important to remember that weather on a planet depends on more than sunlight. It is also shaped by internal heat, rotation, atmospheric composition, and the way energy moves between different layers of gas. Neptune releases more energy into space than it receives from the Sunday. Its internal heat may include energy left over from the planet's formation, along with heat generated by the extremely slow contraction of material under gravity. This energy rises from the deeper layers and helps drive atmospheric motion. Neptune also rotates quickly, completing one turn in about 16 hours. That rapid rotation stretches air currents into long bands and helps organize the wind systems around the planet. So even though sunlight is weak, Neptune still possesses enough internal energy to sustain a violently active atmosphere. Neptune's blue color comes partly from methane in its atmosphere. Methane absorbs more red light, allowing a greater portion of the blue light to return to space. However, the deep blue color commonly seen in Voyager images should not be interpreted as the exact shade human eyes would perceive under every condition. Some images were processed to emphasize differences between cloud layers and atmospheric structures. Even so, the blue color reflects a genuine characteristic of the planet. It is not evidence of an exposed ocean, but the result of light traveling through extremely deep layers of gas. Voyager also resolved a long-standing question about Neptune's rings. Before the encounter, observations from Earth sometimes detected only short segments of material, leading scientists to suspect that Neptune might possess isolated arcs rather than complete rings. But when Voyager photographed them with the sun shining from behind and used long exposures, faint material gradually became visible around the entire planet. The arcs were not separate ring segments. They were denser concentrations of material located within complete rings that were extremely dark, thin, and unevenly distributed. These rings are difficult to observe from Earth because their material reflects very little light. From billions of kilometers away, even large telescopes struggle to distinguish a faint band of dust from Neptune's much brighter glow. Voyager had the advantage of being nearby and could position its cameras at angles where sunlight passed through the material, making the dust particles easier to see. Once again, the spacecraft demonstrated that ring systems were not unique to Saturn. Every giant planet has rings of material, though they differ greatly in brightness, composition, and structure. Yet, as at Jupiter and Saturn, the greatest surprise came from a moon. Triton is Neptune's largest satellite, with a surface so cold that nitrogen can freeze solid on the ground. Temperatures there fall to around -235 degrees Celsius, making Triton one of the coldest worlds ever directly measured in the solar system. From a distance, such a place might seem completely motionless, but when Voyager photographed the southern hemisphere, scientists noticed long dark streaks across the surface and plumes of material rising into the moon's thin atmosphere. Some of these plumes rose nearly 8 kilometers before winds carried the dark material more than 100 kilometers away. These were not volcanoes in the familiar earthly sense. No streams of glowing molten rock flowed across the surface. In Triton's extreme cold, substances such as nitrogen, methane, and carbon monoxide can play roles similar to those of water and water vapor in colder geological processes. Pressurized nitrogen gas beneath the surface may escape through fractures, carrying dust and dark material upward into the extremely thin atmosphere. The exact mechanism is still being studied, but Voyager proved that geological activity does not always require hot lava. It is possible that Triton's weak sunlight passes through translucent nitrogen ice, warming darker material below and causing gas pressure to build. Once the pressure becomes high enough, the gas forces its way upward, producing jets like natural geysers. Even when the available energy is very small, processes operating under unusual conditions and over long periods can still create visible changes. Triton therefore repeated the lesson Voyager had begun to reveal at Io and Europa. A world far from the Sun is not necessarily a dead world. Triton's orbit tells another story. Most large moons travel around their planets in the same direction that the planet rotates, reflecting their formation within the disk of material that originally surrounded the planet. Triton moves in the opposite direction. It is the only large moon in the solar system with such a retrograde orbit. This is strong evidence that Triton may not have formed alongside Neptune. It may once have been an independent body in the outer solar system, similar to objects in the Kuiper belt, before being captured by Neptune's gravity. Such a capture would not have been simple. Triton would have needed to lose orbital energy through an interaction with another object or with a former system of moons around Neptune. That process may have disturbed or destroyed many of Neptune's original satellites while placing Triton into a highly elongated initial orbit. As tidal forces gradually made the orbit more circular, Triton's interior may have been strongly flexed and heated. This could help explain why its surface preserves evidence of a complex geological history, even though the moon is now unimaginably cold. Voyager clearly observed only part of Triton. Its images revealed bright plains, depressions, regions with a texture resembling cantaloupe rind, and dark streaks left behind by the plumes. But the spacecraft could not enter orbit to map the entire moon, monitor the jets through multiple seasons, or directly measure its internal structure. As with Miranda, the images opened the door to a new world, and then Voyager had to leave before every question could be answered. The trajectory past Triton was chosen with great care. Voyager 2 first passed Neptune, whose gravity then bent the spacecraft's path downward, below the plane in which the planets orbit. Just a few hours after its closest approach to the planet, Voyager flew near Triton and captured its highest resolution images of the moon. But this route also confirmed that no other planets lay ahead. The spacecraft had used its final gravity assist to leave the planetary region in a new direction. As Voyager 2 looked back, Neptune gradually shrank into a blue sphere suspended in the darkness. Triton receded into the distance, its plumes continuing to erupt with no camera left to watch them. The faint rings became nearly invisible once again, while powerful winds kept sweeping clouds around the planet. After 12 years, Voyager 2 had accomplished what no one could be certain it would achieve when it was launched, flying close to all 4 giant planets of the solar system. The planetary grand tour ended there. The cameras remained operational for a short time, but there were no more large worlds ahead to photograph at close range. Voyager 2 was placed into a power-conserving mode and began a new mission toward the boundary where the solar wind meets the interstellar environment. From a spacecraft built to observe planets, it gradually became a small scientific station, drifting through the outermost reaches of the Sun's influence. Beyond Neptune lay an emptiness difficult to grasp using familiar measures. No more planetary disks grew larger in the camera, and no more moons appeared for a few hours before vanishing behind the spacecraft. Sunlight continued to fade, signals took longer to reach Earth, and the colorful images of the age of planetary discovery gradually gave way to invisible streams of data. But before the eyes of the 2 Voyagers were shut down forever, humanity wanted them to perform one final task. Voyager 1, by then already far beyond the planets, was instructed to turn its camera back toward the place where the journey had begun. In that image, Earth was no longer a vast world of oceans, continents, and cities. It was only a pale blue dot smaller than a single pixel, suspended within a ray of light and carrying the entire history of humanity. On the 14th of February 1990, Voyager 1 turned its cameras back toward the solar system. By then, the spacecraft was nearly 6 billion kilometers from Earth, so distant that even light needed more than 5 hours to travel the distance one way. From there, Earth no longer appeared as a vast blue planet covered with oceans, white clouds, and continents. It had nearly vanished into the emptiness, reduced to a tiny point of light suspended within a faint band of brightness. The idea of looking back at the solar system was not part of Voyager 1's primary mission when it launched in 1977. The spacecraft had been designed to fly past Jupiter and Saturn, observing their atmospheres, rings, and moons. After completing those encounters, Voyager 1 left the plane in which most of the planets orbit and began traveling toward the outer reaches of the solar system. Its cameras were still working, but there were no more large planets ahead for the spacecraft to approach. Astronomer Carl Sagan repeatedly urged NASA to turn the cameras back and capture a family portrait of the solar system. The idea sounded simple, but carrying it out was not entirely easy. From Voyager's position, the sun was still an intensely bright source of light. If the cameras pointed too close to it, the glare could damage the instruments or overwhelm the much fainter planets. The mission team had to calculate the viewing angles, exposure times, and sequence of observations so the spacecraft could photograph several planets without placing the cameras at unnecessary risk. Voyager 1 ultimately captured a series of images that included the Sun and 6 planets. Mercury was too close to the Sun to observe safely, Mars was hidden in scattered light, and Pluto was too small and faint to appear clearly. The remaining images did not form a single seamless photograph like a family standing together. Each planet occupied a different position in the sky and had to be photographed with its own settings. The frames were later arranged to show their relative positions within the solar system. Among those images, Earth appeared so small that it was almost impossible to recognize. The planet's point of light occupied only a fraction of a pixel. Without knowing exactly where to look, a viewer could easily miss it. Earth lay within a pale band of light crossing the frame, produced when sunlight scattered inside the camera system. That band was not a real structure in space, nor was it a special beam shining directly on the planet. It was simply the result of how light entered the imaging instrument. This does not make the photograph any less meaningful. If anything, the scattered light and visual interference make Earth even harder to notice. A planet containing billions of people, mountain ranges, oceans, and cities had become a tiny mark among features that, in another photograph, might have been dismissed as unwanted noise. Earth appeared so small, not because it was physically smaller than the other planets, but because distance had reduced its apparent size. When an object is very far away, the light coming from it occupies only a tiny angle within the field of view. Voyager's camera had limited resolution, so the entire Earth was no longer large enough to extend across several pixels. The planet's light was compressed into an area smaller than a single pixel, making its colors and surface details impossible to distinguish. No continents could be seen. There were no recognizable clouds, oceans, or curved horizon. Nothing in the image directly revealed that life existed on that point of light. Without the accompanying data, an observer from somewhere else might never know that it was a planet with an atmosphere, liquid water, and countless living organisms. The pale blue dot was therefore not Voyager's most data-rich photograph. It did not reveal the swirling currents of the Great Red Spot, the fractures across Europa, Miranda's patchwork terrain, or the moving clouds of Neptune. From the perspective of studying a planet in detail, the image provided very little information. Its value lay somewhere else, in scale. Voyager had traveled far enough to place Earth within a setting from which humanity rarely sees itself. From the planet's surface, Earth seems to be the entire world. The horizon stretches outward, the sky covers everything above, and nearly every human journey takes place on the ground or within a very thin layer of atmosphere. But from nearly 6 billion kilometers away, that entire living space contracts into a point of light that can barely be distinguished. Every city ever built lies on that dot. Every road, home, field, and forest exists within an area smaller than 1 pixel. Civilizations that rose and disappeared, voyages across oceans, scientific discoveries, and every personal memory have all remained within that point of light, apart from the very small number of spacecraft humanity has sent beyond it. The smallness seen in the photograph does not mean that events on Earth become meaningless. It simply reveals that they all exist together within an extremely limited space. Borders, distances, and differences that seem immense from the ground are completely invisible from Voyager's position. There are no boundaries between nations, no signs of great cities, and no colors revealing which places are wealthy and which are poor. The image also makes the fragility of our living environment clearer. Earth does not appear surrounded by a thick, obvious shield. The atmosphere that maintains temperature, liquid water, and life is only a very thin layer around the planet. From such a great distance, it cannot be seen at all. Within the vastness of space, every living thing humanity has ever known depends on the conditions preserved on that tiny point. Yet this chapter does not need to turn the pale blue dot into a long speech about humanity. The perspective itself is powerful enough. We need only place two images beside each other. Earth seen from its surface, where the horizon seems to stretch without end, and Earth seen from Voyager, where the entire planet nearly disappears. The distance between those viewpoints shows how profoundly people can change their understanding of themselves simply by standing somewhere else. The series of photographs taken on the 14th of February 1990 also marked the end of an era. After completing the Solar System family portrait, Voyager 1's cameras were turned off. This was not because they had suddenly failed, but because of a deliberate decision. There were no longer any suitable planetary targets ahead, while the spacecraft's available power was steadily declining. Keeping the cameras active would have consumed electricity and heat for instruments with little remaining opportunity to produce useful data. Voyager 2's cameras had already been shut down after its Neptune encounter in 1989. Over more than a decade, the two camera systems returned tens of thousands of images, transforming distant points of light into worlds with storms, rings, volcanoes, cliffs, and atmospheres. Once the cameras stopped operating, Voyager could no longer produce images that human eyes could understand immediately. But turning off the cameras did not mean that the spacecraft had stopped doing science. A spacecraft carries many instruments, each suited to a particular environment and a different stage of the journey. Cameras are especially useful near planets and moons, where sunlight reflected from surfaces and clouds can form recognizable images. In the emptiness between the planets, especially after leaving the major worlds behind, the cameras would see little more than a dark sky filled with stars that appeared almost unchanged. The instruments that measured magnetic fields, plasma, and high-energy particles were better suited to this new stage of the mission. They did not produce colorful images, but they could sense the invisible components surrounding the spacecraft. A magnetic field cannot be seen with the eyes, yet it has both direction and strength. Plasma in space is extremely thin, but its oscillations can still be measured. High-energy particles do not form a visible landscape, but when they pass through an instrument, they leave signals that help scientists understand how the surrounding environment is changing. Voyager, therefore, changed from a pair of eyes into a listener. During the planetary era, it told its story through light. After the pale blue dot, it spoke through small streams of numbers that returned to Earth after traveling for many hours. This new form of storytelling was less visual, but it carried humanity into a region that cameras could barely describe. The pale blue dot was also a farewell to the solar system, as humanity was accustomed to seeing it. Voyager 1 looked back one final time, recorded the positions of the planets that had once lain ahead, and then continued outward. From that point on, Earth, Jupiter, and Saturn grew even smaller. Even the sun gradually lost its familiar brilliance and became one bright star among many others. The spacecraft had no way of knowing that its photograph would become one of the most frequently remembered images of the space age. It simply carried out a sequence of commands sent from Earth, turning its body, activating its cameras, capturing each frame, and transmitting the data home. The meaning emerged only when humanity saw itself within the result. From an immense distance, Voyager revealed that Earth was not at the center of the frame. The planet lay near the edge of an image, so small that it could easily be overlooked. Yet that tiny place had built the spacecraft, calculated its path, and sent it beyond 4 giant planets. That nearly invisible point of light had become capable of looking back at itself from a distance never reached before. After the final photograph, Voyager continued into a region where its cameras had little left to tell. The colorful planets remained behind, while ahead lay only cold, dark space. To understand where it was, the spacecraft could no longer rely on images. It had to sense invisible particles, plasma, and magnetic fields, then wait for scientists on Earth to recognize the moment it crossed a boundary with no line, no light, and nothing the human eye could see. In 2012, NASA announced that Voyager 1 had entered interstellar space. The news was quickly interpreted in a simpler way. Humanity's first spacecraft had left the solar system. But those two statements do not mean exactly the same thing. Voyager 1 truly crossed an important boundary, where the environment created by the sun gives way to matter between the stars. Yet the spacecraft has not passed beyond everything that could be considered part of the outermost solar system. To understand what Voyager crossed, we first need to view the sun in a different way. Our star does more than emit light and heat. From its outer atmosphere, the sun continuously releases a stream of charged particles into space. This flow is known as the solar wind. It is not like the wind we feel against our skin, because space has no dense atmosphere to create moving air. The solar wind consists of protons, electrons, and other particles traveling at extremely high speeds, while carrying the influence of the sun's magnetic field with them. As this stream spreads outward, it creates an enormous region surrounding the sun and the planets. This region is called the heliosphere. It can be imagined as an invisible bubble inflated by the solar wind within the extremely thin material of the galaxy. Inside the bubble, particles and magnetic fields originating from the sun dominate the environment. Outside lies interstellar space, where the matter between the stars becomes more influential. The heliosphere is not a perfect sphere suspended motionless in the darkness. The sun and the entire solar system are moving through the Milky Way, so this region of influence is subjected to pressure from the surrounding interstellar environment. Its true shape may be distorted, elongated, and constantly changing with the sun's activity. The solar wind does not blow at a perfectly steady rate either. It strengthens, weakens, and carries disturbances associated with the star's activity cycle. After Voyager traveled beyond the planets, it remained inside the heliosphere for decades. Particles from the sun continued to pass the spacecraft even when it had traveled far beyond Pluto's orbit. But the solar wind cannot expand forever with the same strength. As it moves outward, it becomes increasingly diffuse and encounters pressure from interstellar matter. At a certain distance, the flow of particles from the sun begins to slow, becomes compressed, and eventually no longer dominates the surrounding environment as it once did. Voyager 1 and Voyager 2 did not see this boundary with their cameras. No glowing wall, visible line, or physical doorway appeared in front of the spacecraft. Even if Voyager's cameras had still been operating, they would have struggled to capture this moment in an image that humans could easily understand. The boundary between the heliosphere and interstellar space was identified through changes in invisible phenomena: the number of particles, their energy, the density of the plasma, and the properties of the magnetic field around the spacecraft. Before crossing the boundary, Voyager detected many energetic particles originating within the sun's region of influence. As the spacecraft approached the edge, the number of those particles began to decline. At the same time, cosmic rays arriving from beyond the solar system increased. Cosmic rays are not beams of light like visible rays. They are primarily extremely high-energy charged particles produced by powerful events within the galaxy and sent racing through space at tremendous speeds. Inside the heliosphere, the solar wind and its magnetic field partially prevent high-energy particles from the galaxy from entering. The heliosphere does not form a perfect shield, but it influences both the number and the paths of cosmic rays. As Voyager moved outward, that protection gradually weakened. Its instruments began recording more particles from the galaxy and fewer particles originating from the Sunday. The 25th of August 2012 was identified as the date when Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, and entered the interstellar environment. However, that conclusion was not reached at the exact moment the spacecraft crossed. Scientists had to examine the data for several months, comparing changes in particles, magnetic fields, and plasma before enough evidence existed to confirm it. One of the most important measurements came from plasma density. Plasma is a state of matter in which charged particles can move relatively freely. The space between planets and between stars is not completely empty. It contains gas, dust, magnetic fields, and extremely thin plasma. The density of matter is so low that an ordinary room on Earth contains vastly more particles. Yet Voyager's sensitive instruments can still detect the difference. The interstellar environment outside the heliosphere has a higher plasma density than the distant region occupied by the solar wind. Voyager 1 could no longer measure this density directly with all of its original instruments, but its plasma wave system could detect oscillations produced when disturbances passed through the surrounding medium. The frequency of those oscillations allowed scientists to estimate the density of electrons around the spacecraft. The results matched predictions for the interstellar environment, strengthening the evidence that Voyager 1 had traveled beyond the heliosphere. 6 years later, Voyager 2 approached the same kind of boundary from a different direction. The 5th of November 2018 was identified as the date when Voyager 2 entered interstellar space. This spacecraft still had several instruments operating that were no longer available on Voyager 1, allowing it to directly measure the decline of the solar wind during the crossing. Voyager 2's data confirmed many of the features previously recorded by Voyager 1, while also showing that conditions at the two locations were not exactly the same. This was important because the heliosphere is not a uniform shell. Voyager 1 exited along a path north of the planetary plane, while Voyager 2 followed a different direction to the south. The two spacecraft encountered the boundary at different distances. The particles and magnetic fields at those locations also displayed certain differences. Together, these measurements revealed that the shape and structure of the heliosphere are far more complex than a simple spherical bubble. However, the two spacecraft still represent only two measurement points within a region tens of billions of kilometers wide. Imagine trying to determine the shape of an ocean using only two buoys placed in different locations. They could reveal the water level, the direction of the current, and the temperature where they were floating, but they would not be enough to map the entire coastline. Voyager has allowed humanity to touch two parts of the heliosphere's boundary, but it cannot yet reveal the exact shape of that entire region in every direction. This is where it is important to distinguish between what Voyager actually measured and how scientists interpreted those measurements. The spacecraft recorded a sharp decline in particles originating from the Sun, an increase in cosmic rays from the galaxy, a change in plasma density, and surrounding conditions that differed from those it had encountered before. From this evidence, scientists concluded that Voyager had crossed beyond the region, dominated by the solar wind, and entered interstellar space. But this boundary should not be imagined as a fixed wall. Particles can move across it in both directions. The Sun's influence can still travel beyond it in the form of disturbances. The magnetic fields on either side do not necessarily change in a simple or predictable way. The heliopause is a dynamic transition zone shaped by both the Sun and the interstellar environment, not a sealed doorway that closed behind Voyager after it crossed. So, has Voyager left the solar system? The answer depends on which boundary we use to define it. If we mean the region of plasma created by the solar wind, then Voyager 1 and Voyager 2 have left it. They are now operating within the interstellar environment and are the first two spacecraft to make direct measurements there. But if we mean the region still governed by the Sun's gravity, both spacecraft remain deep inside it. The Sun's gravitational influence extends far beyond the heliosphere. Beyond the planetary orbits and the Kuiper belt, scientists believe there is an immense region of icy bodies known as the Oort cloud. It is thought to be the source of many long-period comets. The Oort cloud has never been directly observed as a complete structure, but the motion of comets and models of solar system formation suggest that it may extend across an enormous distance. Voyager has not yet reached the inner region of the Oort cloud. At its present speed, the spacecraft may need hundreds of years to enter the nearer part of this region and tens of thousands of years to cross its full predicted extent. Throughout most of that time, Voyager will still be moving under the gravitational influence of the Sun, even though the pull will be extremely weak. This does not diminish the significance of the milestones reached in 2012 and 2018. Leaving the heliosphere remains an unprecedented achievement. Before Voyager, scientists studied this boundary mainly through distant observations, computer models, and indirect measurements. The two spacecraft carried instruments directly into the region, allowing humanity to sense the environmental transition one particle at a time. The interstellar space through which Voyager is now traveling is not completely empty. It contains matter from earlier generations of stars, the magnetic field of the galaxy, high-energy particles, and thin clouds of gas. Some of the atoms in this environment may once have existed inside stars that died long ago. Voyager is moving through the vast material between star systems, even though the nearest star remains almost unimaginably far away. Crossing the heliopause produced no sound, vibration, or flash of light. No one was there to watch the spacecraft pass through. On Earth, scientists received only streams of numbers that had taken many hours to return. Individual measurements changed gradually, and then a picture began to emerge. Particles from the sun declined, cosmic rays increased, the plasma became denser. The space surrounding Voyager had changed. It was a threshold that could only be recognized after the spacecraft had already crossed it. Voyager continued moving just as before, with no sudden change in speed and no awareness that humanity had named a new milestone in the history of exploration. But from that moment onward, Voyager was no longer merely studying the outer reaches of the solar system. It had become a small scientific station directly measuring the environment between the stars. Just as Voyager entered a region where no other spacecraft had ever operated, the resources keeping it alive continued to decline. Each year, its generators produced less electricity. The instruments that helped confirm the boundary of the heliosphere began facing the possibility of being shut down one by one. The spacecraft had crossed into a new scientific frontier, but the time remaining for it to describe what lies beyond was shrinking with every watt of power. Voyager will not die because it runs out of fuel to keep moving. In the near vacuum of space, the two spacecraft can continue drifting silently through the momentum they received from their rockets and planetary flybys. What is gradually running out is not the distance ahead, but the electricity needed to keep the computers, scientific instruments, radio transmitters, and heating systems operating. After nearly half a century, every watt of power aboard Voyager has become part of a survival equation. Each spacecraft carries 3 radioisotope thermoelectric generators. These are not miniature nuclear reactors. Inside them is plutonium-238, a material that naturally releases heat as it decays. Special pairs of materials convert part of the temperature difference into electrical current, providing power even when sunlight has become too weak for solar panels to operate effectively. The amount of heat produced declines each year, while the components that convert heat into electricity have also deteriorated after decades of operation. As a result, each Voyager loses about 4 watts of usable power annually. 4 watts may not sound significant, roughly the power consumed by a very small light bulb. But when that loss continues for nearly 50 years, enough electricity disappears to force the mission team to decide which instruments may remain alive and which must fall silent. The power problem is not as simple as counting the scientific instruments and turning them off one by one. Voyager needs electricity to receive commands, transmit signals, keep its antenna pointed toward Earth, and warm critical components. The fuel used for attitude control is a separate issue from electrical power. Small thrusters rotate the spacecraft and keep its large antenna aimed at Earth. If a fuel line freezes or the thrusters can no longer function, Voyager may gradually turn away, causing its signal to miss the antennas listening from home. For many years, the mission team conserved power by shutting down systems that were no longer needed during the interstellar phase. The cameras completed their work after the planetary encounters and were turned off in 1989 and 1990. Spectrometers, ultraviolet instruments, and the planetary radio astronomy system were also shut down over time. Each decision created a small reserve of power, allowing more important systems to continue operating. Voyager survived for so long not because it possessed an unlimited energy supply, but because humanity continually reduced the mission to match the electricity that remained. Once the largest electrical loads had been removed, the choices became more difficult. The team began switching off heaters that had once been considered essential. This was a calculated gamble. Turning off a heater saved electricity, but forced an instrument to operate at temperatures lower than those tested on Earth. Some components continued working far longer than expected, yet no one could be certain that the next reduction would not cause a fuel line to freeze or an instrument to stop responding. By 2025, NASA had entered a more difficult phase, shutting down instruments that were still working properly and still capable of producing unique scientific data. On the 25th of February 2025, Voyager 1's cosmic ray system was turned off. That instrument had helped identify when the spacecraft crossed beyond the heliosphere by tracking the decline of particles from the Sun and the increase of high-energy particles from the galaxy. Because the mission needed to continue, one important sense had to be sacrificed to preserve electricity for the others. On the 24th of March 2025, Voyager 2's low-energy, charged particle instrument was also switched off. Then, on the 17th of April 2026, the same type of instrument aboard Voyager 1 stopped operating after nearly 49 years of service. It had measured ions, electrons, and cosmic rays while detecting regions of different particle densities beyond the heliosphere. When the shutdown command was sent, the instrument had not failed, nor had it finished answering every scientific question. It had simply reached the next position in a sequence of power reductions planned years in advance. According to NASA's status update of the 17th of April 2026, Voyager 1 has 2 scientific instruments still operating, the magnetometer and the plasma wave system. Voyager 2 has 3: the cosmic ray system, the magnetometer, and the plasma wave system. These instruments do not return images, but they can still sense magnetic fields, plasma oscillations, and high-energy particles in the interstellar environment. No other spacecraft can currently collect the same data at such distances. The process can be imagined as a traveler moving far into the night and gradually surrendering different senses in order to preserve strength. First, Voyager lost its sight when the cameras were turned off. Later, it lost the ability to analyze certain wavelengths and certain kinds of particles. Eventually, all that remained was the ability to sense magnetic fields and listen to the plasma vibrating around it. Each instrument that falls silent narrows the picture of interstellar space, yet also extends the time during which the remaining instruments can continue telling their story. The decision about which instrument to shut down is never made during a hurried meeting. Scientists evaluate which kinds of data remain unique and how much electricity each instrument consumes. Engineers must also consider the risk involved in the shutdown itself. An instrument that has operated for decades may never be able to start again. A command takes more than 20 hours to arrive, and the response requires just as long to return. Once the decision is carried out, there is no immediate undo button. NASA hopes that these conservation measures may allow at least one instrument on each spacecraft to continue operating into the 2030s. But this is not a guaranteed deadline. Voyager has endured nearly 50 years of radiation, extreme temperatures, and aging components. A computer could develop a fault, a transmitter could weaken, a thruster could become blocked, or available power could fall faster than the team can manage. No one can promise that the signal will survive until any specific date. What is remarkable is that Voyager will continue traveling even after every instrument has been turned off. Its motion does not depend on electricity in the way a car depends on fuel. When the generators can no longer provide enough power, Voyager will not stop in the middle of space. It will simply lose the ability to measure, correct its orientation, and call home. The spacecraft will continue drifting among the stars, but its existence will no longer be confirmed by streams of data appearing on screens on Earth. For that reason, the end of the mission may not come with an explosion or any dramatic moment. One day, the antennas of the Deep Space Network may still turn toward the correct region of the sky, but the familiar signal will not appear. Engineers may resend commands, try backup modes, and wait nearly 2 days for each attempt. If no answer returns, distance will have transformed a small malfunction into complete silence. Until then, every watt that can be preserved matters. It may provide a few more weeks of magnetic field measurements, several more months of listening to plasma, or one additional opportunity to record a wave from solar activity moving into interstellar space. Voyager can no longer explore many worlds at once, but its location makes every measurement irreplaceable. The culmination of Voyager's story does not lie in keeping every system alive until the final moment. It lies in the art of accepting the loss of one part so that another can continue. Turning off a camera allows another instrument to survive longer. Shutting down a heater preserves power for the transmitter. One scientific instrument falls silent so that two others may continue returning signals unlike any ever received before. This is not the failure of the spacecraft, but the way a finite mission extends its presence in a place no one has ever reached. One day, the final instrument will also fall silent, and the communication link that endured for nearly half a century will come to an end. But even when Voyager no longer has enough power to call Earth, it will still carry a message that never depended on its transmitter. A metal record containing the images, sounds, and greetings of the world that sent it on its way. Voyager's signal can exist only as long as the spacecraft has enough electricity to operate its computers, keep its antenna pointed toward Earth, and transmit across the emptiness of space. One day, the available power will fall below the level required, and that faint voice will disappear. Yet attached to both Voyager 1 and Voyager 2 is a message that needs no electricity, sends no signal, and does not actively call out to anyone. It is the Golden Record, a gold-plated disc carrying a brief portrait of Earth. The Golden Record is made of copper, coated with gold, and enclosed within a protective cover. Beside it is a playback stylus, along with symbols explaining how the record might be used. When the two Voyagers left Earth in 1977, no one knew how long they would remain operational. But the record was not prepared only for the years when the spacecraft could still transmit. It was designed to endure even after every electronic system had fallen silent. The Golden Record is not a radio transmitter. It does not continuously send greetings into the space around it, nor can it announce its own location. In the near vacuum of space, the sounds recorded on the disk do not play by themselves. To discover what it contains, a recipient would have to encounter Voyager by chance, recognize the disk as a storage medium, understand the symbols on its cover, and play it correctly. That chain of conditions alone reveals how extraordinarily small the chance may be that the message will ever be opened. The contents of the record were selected by a team led by Carl Sagan. They faced a question that was almost impossible to answer. If only one small object could tell the story of Earth, what should it contain? It could not include all of human history, every culture, every living species, or every emotion that had ever existed. The Golden Record is therefore not a complete library. It is a carefully chosen collection, an attempt to leave a few traces that might help a recipient imagine the world that created Voyager. The record contains images related to mathematics, physics, chemistry, living organisms, animals, plants, human beings, and everyday activities on Earth. They are not stored like the digital image files we use today. The information is encoded as continuous signals within the grooves of the record. If decoded correctly, those signals can be reconstructed into images. In simple terms, analog data changes continuously with the shape of a signal. As a stylus travels through a record's groove, it vibrates and converts tiny variations into sound. The Golden Record uses a similar principle to store both audio and images. A recipient would not need to understand human software, file formats, or operating systems, but they would still have to discover how to transform those tiny grooves into information that could be seen and heard. The audio section contains greetings in many languages, along with natural and familiar sounds from Earth. There are ocean waves, wind, thunder, birds, whales, and many other sounds of life. Among them are footsteps, a heartbeat, vehicles, and traces of human beings going about their lives on the planet. Music from many cultural traditions was also placed on the record, reflecting the fact that people communicate not only through words, but also through rhythm, melody, and emotion. There is no need to describe the entire collection to understand what the team hoped to send. We need only imagine an unfamiliar recipient lowering the stylus and hearing, one after another, rain, ocean waves, animals, human voices, and music. These sounds do not prove that Earth is a perfect world. nor do they tell the complete story of human conflict, loss, and limitation. The Golden Record is a selected portrait, not a complete account of the civilization that created it. That incompleteness reveals what humanity chose to preserve. When only a tiny selection could represent an entire planet, the team chose life, language, music, movement, and the capacity for awareness. They did not know whether a recipient would possess ears like ours, perceive light as human eyes do, or understand music at all. But they believed that a civilization capable of finding a spacecraft in interstellar space might recognize certain universal laws of physics. The symbols on the record's cover were designed around that belief. One diagram shows the position of the stylus and how the disc should be played. Other symbols explain its rotation speed and how the images should be reconstructed. A circle appears at the beginning of the image sequence as a test. If it is decoded as an oval or a distorted shape, the recipient may realize that the data is not yet being read correctly. To identify the place where Voyager began its journey, the cover also carries a map based on pulsars. Pulsars are rapidly rotating neutron stars that emit regular pulses, like natural lighthouses within the galaxy. The map shows the position of the Sun relative to a group of nearby pulsars. Because their pulse rates change slowly over time, a sufficiently knowledgeable recipient might use them to trace the spacecraft back to the place and era from which its journey began. This is not a simple address, like a street name or a point on a map. The stars are all moving, and the distances between them are immense. A recipient would have to identify the correct pulsars, understand the symbols, and reconstruct the Sun's position from a time far in the past. Yet, in a galaxy with no shared navigation system, these natural lighthouses are among the few landmarks that might be recognizable from many different locations. Even with all these instructions, there is no guarantee that the message would be understood. Humanity had to assume that the recipient would understand atomic physics, recognize how to use a playback stylus, and interpret two-dimensional diagrams. Another civilization might have developed technology along an entirely different path. Even if it found Voyager, the record might remain nothing more than a strange metal object that no one knew how to open. The greater difficulty lies in the distance. Interstellar space is so vast that Voyager must travel for far longer than the entire history of modern civilization before passing relatively close to another star system. Yet even close, in astronomical terms, may still mean an enormous distance, far too great for the spacecraft to be easily detected. Voyager is not traveling directly toward a planet known to support life, nor does it carry a beacon that will continue operating forever to attract attention. The Golden Record should therefore not be understood as a letter certain to reach a recipient. It is more like a small bottle released into an ocean so vast that there may be no opposite shore. The meaning of the act does not depend entirely on whether the bottle is ever found. Choosing to send it forced humanity to look back at itself and decide what was worth preserving when everything could not be carried along. After Voyager loses power, the record will continue its journey. The spacecraft does not need its engines to operate continuously, because in the near vacuum of space there is almost no resistance to bring it to a stop. It will keep moving under the influence of gravity, circling the Milky Way alongside stars, clouds of gas, and countless other objects. Voyager will no longer be an active scientific station. It will become a silent object carrying traces of Earth. Voyager's achievements are therefore more than the images and streams of data it sent home. The two spacecraft revealed that Io is still erupting. Europa has a young and fractured icy surface. Saturn's rings are always in motion. Miranda carries a patchwork geological landscape, and Triton still produces plumes on an extraordinarily cold world. They also directly measured the invisible boundary where the solar wind gives way to the interstellar environment. The Golden Record looks in the opposite direction. While Voyager's instruments observe the universe and return their findings to Earth, the record attempts to tell the universe what created the spacecraft. One side of the story is about what humanity discovered out there. The other is a very brief account of where we began. Perhaps no one will ever hear the rain, the greetings, or the music preserved within those grooves. The Golden Record may continue circling the galaxy longer than every city and structure that has ever existed on Earth without ever meeting a recipient. Yet it still retains its meaning as a human choice, to send a portrait of life into the darkness without knowing whether anyone is waiting on the other side. One day, Earth will send a command and receive no reply. The antennas will still point toward the region of the sky where Voyager is traveling, but the familiar signal will not appear. Yet that silence cannot erase what the two spacecraft helped humanity see. Nor can it stop the journey of the Golden Records as they continue carrying the voice of a small world among the stars. Returning to the control room where the story began, a command is sent into the sky. The signal leaves the antenna, crosses the cold and dark expanse of space, and takes nearly a full day to reach Voyager. If the systems aboard the spacecraft still have enough power to receive, process, and answer it, the engineers will wait for a similar length of time once again. After almost 2 days, a small stream of data may appear on the screen, confirming that somewhere unimaginably far away, the spacecraft is still operating. But eventually, there will come a moment when the screen no longer changes. That silence will not arrive with an explosion or a violent final moment. Voyager will not stop in the middle of space. When its power falls below the level required, the scientific instruments will stop taking measurements. The transmitter will no longer be strong enough to send a signal, and the attitude control system may lose the ability to keep the antenna precisely aimed at Earth. The journey will continue. Only the thread of communication between the spacecraft and the world that created it will gradually come to an end. What Voyager leaves behind will not disappear with its final signal. Before the two spacecraft arrived, many planets and moons in the outer solar system were little more than distant points of light seen through telescopes. After the flybys, they emerged as worlds with their own atmospheres, landscapes, weather, and histories. At Jupiter, swirling cloud bands, enormous storms, and a faint ring system gradually came into view. Io shattered the idea that distant moons were merely cold, lifeless rocks by revealing active volcanic plumes rising from its surface. Europa opened a different question. With its young ice, relatively few impact craters, and long fractures, suggesting that an entirely different environment might exist below. Saturn revealed that its seemingly perfect rings were actually made of countless particles of ice and rock, each traveling along its own orbit. Small moons could shape the edges of the rings, open gaps, or pull material into intricate structures. Enceladus revealed a bright and relatively young surface, while Titan concealed every landscape beneath a dense orange atmosphere. Voyager 2 alone continued onward to the two most distant planets. Uranus appeared with an axis tilted almost completely sideways, a system of dark rings, and a magnetic field displaced from the planet's center. On Miranda, towering fault scarps, deep canyons, and patchwork regions of terrain revealed that even a small moon could endure a violent geological history. Farther still, Neptune sustained powerful winds, despite receiving very little sunlight, while frozen Triton continued sending material above its surface. This is Voyager's planetary legacy. The two spacecraft transformed distant points of light into worlds with motion and histories of their own. Through these discoveries, humanity learned that distance from the Sun is not the only factor determining whether a celestial body remains active or becomes motionless. Gravity, internal heat, and orbital motion can still sustain powerful processes in places where sunlight has faded to a faint glow. Voyager's second legacy lies beyond the planets. Voyager 1 and Voyager 2 became the first instruments to directly measure the environment outside the heliosphere. No glowing boundary or physical wall marked the transition. Only through changes in particles, plasma density, and magnetic fields did scientists recognize that the region dominated by the solar wind had been left behind. These measurements cannot be fully replaced by telescopes on Earth because they come directly from the place where the interstellar environment begins to take control. But perhaps Voyager's deepest legacy lies in the way its journey taught humanity to look back at itself. The pale blue dot revealed an Earth so small that it nearly disappeared within a beam of scattered light. The golden record carries rain, music, greetings, and images of life. Even though it may never be found, one photograph looking back toward home and one record facing outward into the darkness both ask the same question. Within a universe this vast, what do we hope to understand about the place where we began, and what do we wish to leave behind after we have passed through? Voyager is not immortal. Time, radiation, and the extreme conditions of space will eventually alter the materials from which the spacecraft were made. In the distant future, their paths may also be influenced by passing stars or other gravitational regions. Yet before that happens, the two Voyagers may continue carrying traces of a civilization for longer than any city or structure that has ever existed on Earth. Voyager has traveled too far ever to return, but every signal it sent back helped humanity see the place where the journey began more clearly. Perhaps that is the deepest meaning of every voyage of exploration. Not only to discover the worlds waiting ahead, but also to learn how to look back at the world that first sent us on our way.